Okay, so for this first question, we are asked to recalculate the theoretical density for cesium chloride, and relevant parameters are given to us in the problem. So first we start with the structure of the cesium chloride. So it is two simple cubic structures embedded in each other, or you draw it as if you're drawing a body-centered cubic structure. So this is your z-axis, this is your x, y, and then we place the ions in the structure. So these ions, the corner atoms, belongs to the cesium plus, and the chloride ion sits inside. So that is what the structure looks like for an ionic crystal, a ceramic, a salt. So the geometric relation for this structure, if you observe between the these two opposite corners of the cube, if you draw the body diagonal in 3 dimensions, you will see that a square root 3 is going to be equal to 2 times the radius of the cesium ion and 2 times radius of the chloride ion. Where did we get this a square root 3? If you draw the cube itself alone, then draw the body diagonal, which is the diagonal between two opposite corners here. Now this is the edge length A, and the edge perpendicular to this one is going to be the face diagonal, and face diagonal has the value a square root 2. So these are perpendicular to each other in 3 dimensions, and so we have a square root 3. The best way to explain this is actually using a cube. So I have this Rubik's cube here. As you can see, between the opposite corners we have the body diagonal going from here coming out there, and the edge is perpendicular to the face diagonal. So after that quick demonstration, now we can move on with our calculation. So the theoretical density is asked. Since this is a structure with 2 different species, we write number of cesium ions times the atomic weight of cesium plus atomic number of chloride ions times the atomic weight of chloride divided by the Avogadro's number times the volume of the unit cell. The volume of the unit cell is going to be a cube, and since we have an expression here now, we can find the volume of the unit cell to be 2 divided by square root 3. From here we leave a alone, and we have this expression. As for the number of the cesium and chloride, so the chloride sits in the middle at the center of the structure, and the cesium are at the corners. So there are 8 corners, and if you inspect this in 3 dimensions, 1/8 of this corner atom is included here. So 1/8, we have 1 atom here, and chloride ion is directly 1. So if we substitute the other given numerical values into the expression. So rho theoretical 1 cesium ion times 132.91 grams per mole times 1 35.45 grams per mole. So the atomic weights are given here, here and here, and the radii of the ions are given. Now we divide that. You should know these constants by heart. And if you calculate the value of A from here, okay, if you leave A alone, we get A as 0.3603 nanometers. So when we are putting it inside here, we directly can substitute the numerical value and convert it to centimeters from nanometers to obtain grams per centimeter cube. Then if you evaluate this expression, you will get 5.979 grams per centimeter cube.